And welcome to the Algebra 2 Jungle, and tonight is our Trig graph finale, and which is always great. It means we're about to cross off another milestone off the checklist here. And tonight we've got two goals tonight that we want to accomplish. It's kind of like two mini lessons packed into one lesson tonight. Number one is we want to do some more modeling with these sinusoidal functions. In other words, we're going to kind of piggyback off of what we did last night and just talk a little bit more, see some more examples. And then number two, we're going to kind of shift gears and we're going to do an introduction to the tangent graph. We've talked a lot about graphing sine and cosine, and together sine and cosine make up what's called that sinusoidal family. But now we're going to introduce you to the tangent graph, who's not necessarily considered a sinusoidal function, although it does have a very cyclic, repeatable behavior like sine and cosine in a sense. So here we go. We've got just a really warm, inviting picture here of warm Arizona, and they said that the temperature in degrees Fahrenheit in a small town in Arizona, X months after January 1st can be modeled by this function right here. So X is the number of months, Y is the temperature in degrees Fahrenheit, and what you'll notice is we've got an amplitude of 30, a frequency of pi over 6, which would then tell us that the period ends up being about 12, and then we've got this vertical shift or a midline at 80. So we're going to see if we can put it all together, and we're going to ask you a few questions relative to this function. And first thing I want to try to do here is get it graphed, and I know you don't quite have a grid this friendly in your notebook, but I think we can take our time and be really, really careful and come up with the best graph possible. Now, before we go any further, let's just confirm that the period is indeed 12, as I indicated. So we've got our 2 pi being divided by our frequency, which was pi over 6. And what you'll notice is that the pi's do cancel, and 2 divided by 1/6 turns out to be 12. So, which makes sense because every 12 months we repeat the cycle all over again, weather-wise. So let's see what we got cooking here. So I've got an axis, and what you'll notice is I've already got it set up so I can go. They said the domain they want to do 0 to 24, so we basically want to show like a 2-year snapshot. And let's see. Let's start with that midline, and we know that the midline's right here at 80. Don't be afraid to make that note off to the side of your notebook. Start with the midline. Start with the midline. Start with the midline. That's always a great place to start. Now the amplitude was 30 degrees Fahrenheit from there, and it was a negative 30, so we're going to reflect the cosine function. And if I start at 80 but I drop 30, that's going to put me right at 50. So my first cosine cycle is going to start at 50, and it's also going to end at 50, which is the only thing that's really not friendly about my grid is that these blocks aren't counting by 1. So I would say if that's 12.5, then 12's right around here, and that's where the first cycle is going to end. So I'm going to come up here, and let's see, I'm going to put my first dot, or my last dot right around there. So the first cycle is going to end right there at 12. So halfway between them is going to be my relative max. So right when x equals 6, I've got to go 30 units above, and that's going to put me right around here. Okay, so from there I'm just going to try to connect the dots as smoothly as I can. Now here's the best news I can offer you. You're more than welcome to make this a calculator active question. So I'm going to try to find 24 here in the meantime, and then halfway between those is going to be 18, which is going to be about right here. Okay, so instead of doing what I'm doing, you could always type that function into y equals and just use all the points that you get in your table and plot those as carefully as you can, and you'll end up with a similar picture. You're going to see 2 complete cycles, and it's an upside down cosine function. Now, building off of that, we want to try to identify the period, the midline, and the amplitude, and then we're going to talk about how to explain what each of those means within the context of this particular story. Now, the period we said was 12 already, so right here, that's 12. And I would describe that as the number of months it takes to complete one cycle before this whole cycle starts over and repeats itself a second time. Now the midline, we've kind of already talked about that bear. That's right here at 80. And within the context of this question, I would say that is the average daily temperature in this small town of Arizona over the course of a 12-month period. So that would be your average temperature. And then the last thing we've got cooking here is the amplitude, which would be the distance from here to here. So that distance right there is my amplitude. And in this case, it happens to be 30 degrees Fahrenheit. And that's just the difference, we would say, between the maximum temperature and the average temperature. You could also spin it a different way and say, well, that's the distance between the minimum temperature and the average temperature, and that would also be 30 as well. Now here's another example of a very useful modeling problem, and similar to the last example, what you'll notice is they're giving us the equation, which is always really, really nice. Last night's examples, we had to create the equations based off of their description. So tonight you could look at it, that's one of the perks tonight. But anyway, the context says that the height of the saddle of a horse on the above carousel can be modeled using this function. So we're just saying, okay, we're measuring the height of this saddle right here relative to how far above the base of the carousel it is. And t represents the number of seconds after the ride started. Now our first question we want to take a look at says, it asks how much time does it take for the horse to complete one cycle of motion and return to its starting height. Well, the key here is when we talk about completing one cycle, that's what we're describing is the period, okay? And so even though they never use the word period, we have to be able to decipher what they're asking for. And we're going to go ahead and we know that the period is 2 pi divided by frequency. So in this case, it's going to be 2 pi divided by pi over 3. We know that those pi's will cancel. And here we could always go back to the calculator and do 2 divided by 1/3. And that'll turn out to be 6. And I'm going to put my units on there. So it takes about 6 seconds for the horse to go up, down, and finish its full cycle and return to its starting height. So 6 seconds there. What else do they want to know? Oh, what's the maximum height? And what's the minimum height? Well, what we know here is our midline is at 4.5, and we can assume that that's measured in feet here, 4.5 feet. And then on top of that, we're seeing the amplitude. The amplitude, the leading coefficient was a 2. So what you do, if you take your midline and you add your amplitude, that gives you your maximum height of 6.5. And if we take our midline and we subtract that amplitude, you'll get your minimum height of 2.5. So just to kind of generalize what we did there. So we're taking our midline and we're either adding the amplitude to get our max height, or we're taking our midline and we're subtracting the amplitude to get our minimum height. Now, be careful here. If that leading coefficient was negative, the amplitude would still be positive 2. So you'd be adding we just want to make sure we take the absolute value of that number before we do the adding or the subtracting, but usually that's not an issue. Okay, so we're done reviewing modeling for the night. We're going to shift gears and kind of almost start over and pretend we've got a second lesson here tonight. And we want to introduce you to the tangent graph. And so here's where I want you to really slow down and take your time. And I want you to be able to brag tomorrow in class about how amazing your tangent graph looks in your notebook. You know, compare it with your neighbors and see who's got the better looking one, but really take your time, and as you're drawing the x-axis, we'll make sure we document -2 pi, -3 pi over 2, -pi, -pi over 2, etc., all the way up to 2 pi. And start with your asymptotes here before you try to draw the curve. Place the asymptote at -3 pi over 2, -pi over 2, positive pi over 2, and then positive 3 pi over 2. So get those asymptotes first. And then be real gentle and smooth and pay attention. Notice how this curve is concave down until we hit the origin. And this is what we call a point of inflection. And it switches to being concave up. And it's going to really hug that asymptote and forever get a little closer, a little closer, a little closer. And then we just repeat that. Now, after you take your time drawing the best tangent curve ever in the history of math, let's talk about where those zeros are located. All right, and let's document that. So we notice we're crossing, we've got an x-intercept at -2 pi, -pi, 0, positive pi, and positive 2 pi. So we could list those. -2 pi, -pi, 0, pi, 2 pi. Or what we could do is we could generalize that and say it's all multiples of pi. And by that I mean any whole number multiples. So, 3 pi would be the next one, 4 pi, 5 pi, 6 pi. If we continued and expanded the domain, we'd see all multiples of pi being zeros. Where are the vertical asymptotes located? Well, those rascals, we can see them clearly here. We talked about where they're located, so let's just document them. Negative 3 pi over 2, negative pi over 2, let's see, positive pi over 2, and positive 3 pi over 2. Now I'd like to generalize those too, because there's more of them if we expanded our window and expanded our domain. So we would say all odd multiples of pi over 2. All odd multiples of pi divided by 2. So the next one that we don't see on our screen would be at 5 pi over 2. And then the next one after that would be 7 pi over 2. Again, 7's odd. Where would the next one be? You got it, 9 pi over 2. So my next question for us is, well, why is tangent undefined at all odd multiples of pi over 2? And this concept of being undefined, it goes hand in hand with vertical asymptotes. So we talked about where the vertical asymptotes are, and that just basically represents that tangent's undefined at those moments. So we're going to try to answer that question. Why is tangent undefined at all the odd multiples of pi over 2? And it all starts with this. Remember when we did the unit circle, we said that the tangent of some angle x is defined as the sine of x divided by the cosine of x. Well, remember how your denominator is not allowed to equal 0? And if it was equal to 0, that would cause the fraction to be undefined. Well, that's exactly what we're going to focus on. We're going to ask ourselves, when is the cosine of x equal to 0? Okay? Now, there's a couple of ways we could tackle this question. Maybe, perhaps, you're really comfortable with the cosine graph. And here's what cosine looks like from 0 to 2 pi, or actually from negative 2 pi to 2 pi. And what you'll notice is there's 4 different x-intercepts where cosine is equal to 0. And those x-intercepts happen to be, this one right here would be negative 3 pi over 2. This one would be negative pi over 2. That one's positive pi over 2. And you start to see the pattern, don't you? That the same place where cosine crosses the x-axis happens to be the location of the tangent's vertical asymptotes. And so there's the correlation. The other thing you could look at is we always like to tie everything back to the unit circle. And as you're going around the circle, with cosine, you're focusing on the x-coordinate. And you're trying to figure out when is the x-coordinate equal to 0. Well, that would be right here because the coordinate's 0, 1, and then the other one would be down here because the coordinate's 0, negative 1. So again, you'd say, well, right here at pi over 2, and right here at 3 pi over 2, and because of the cyclic nature of cosine, you'd see another one at 5 pi over 2 and 7 pi over 2, etc., etc. Here's a great question. When is tangent increasing? Well, ironically, remember how we read a graph from left to right, just like you read a book. Start at the far left, and as you move from left to right, this function's going where? Yeah, he's going up. And then you pick up your pencil, you restart down here, and you move from left to right. And guess what? You're going up. You pick up your pencil, you start over. As you go from left to right, you're going up, going up, going up. When are we increasing? For all values of x, with some minor exceptions. So we'd say we're increasing for all real numbers except at the odd multiples of pi over 2. So we could say except x is not equal to plus or, let's see, erase that a little bit. Let's do plus or minus 3 pi over 2 and plus or minus pi over 2. But everywhere else, it's always increasing. So I'm going to put the word up here, always. In other words, tangent's never decreasing. Here's kind of a blast from the past that we're going to tie in with tangent. We want to know, when is f of x greater than 0? Now remember, f of x represents our y values. And being greater than 0, really what we're doing is we're talking about when is this graph above what? Yeah, above the x-axis. That's what we want to try to document. When are we above the x-axis? And so what I've got here is I'm going to try to bold some of the intervals. So starting right here all the way up, so that would be from negative 2 pi to negative 3 pi over 2. My next interval is from negative pi to negative pi over 2. And then I'm going from 0 up to pi over 2. Let's see, then we'll go from pi to 3 pi over 2. And I think that covers all 4 of my mini intervals where the graph is above the x-axis. Of course, if they turned it around and they said, well, when is f of x less than 0, now we'd be focusing on the parts that are below, and we'd try to do these little rascals right here. Over my past experiences with the tangent graph and introducing it to students for the first time, I've decided that focusing concavity is the #1 factor that helps us draw really clean, accurate graphs. And so remember, concave up is the concept of a function kind of looking like a smiley face, or at least a portion of it. Concave down is more of your frowny face. And points of inflection are where we change concavity. It's a moment where we transition from concave up to concave down. So let's see if we can document all of these as quickly as we can here. So again, concave up, what you have here is you have half of a smiley face. And then again here you've got half of a smiley face. So ironically, and this is just a coincidence, this function happens to be concave up every time that it's above the x-axis, it's concave up. So I'm just going to re-document the same intervals that I used on the last slide. Now as far as concave down goes, now we're looking for kind of the frowny face, and what you'll notice is this section right here is kind of half of a frown. We've got another half of a frown, another half of a frown, and another half of a frown. So all of those sections, they kind of bend in such a way that we call the function concave down. So the first one's from negative 3 pi over 2 to negative pi. The second interval is from negative pi over 2 to 0. The third interval is from pi over 2 to pi. And the fourth and final interval is from 3 pi over 2 to 2 pi. Alright, now for the point of inflections. Points of inflection would be right here where we change concavity, where we made that switch or that transition from being concave up to concave down and vice versa. And those just ironically happen to coincide with the zeros. That's not true for all functions, but ironically it is true for the tangent graph. So I'm just going to list all of those x values that correspond to those points, and these would be our points of inflection. So one of our themes here while we introduce you to the tangent function is that we're kind of tying it in with a lot of older concepts from earlier in the year. And we want to now tie it in with average rate of change. And when we see average rate of change, the formula that I want you to think of is just basically our very simple slope formula that is f of b minus f of a, which kind of measures our change in y or our rise, divided by b minus a, which measures our change in x or our run. And so what I'm thinking is I need f of pi over 4 minus f of 0 all over pi over 4 minus 0. Now when I say f of pi over 4, what I'm really saying here is because we're dealing with a tangent function where f of x equals the tangent of x, f of pi over 4 is the tangent of pi over 4 minus the tangent of 0. And of all those trig values we had to memorize, I'm going to tell you tangent of pi over 4 is our friendliest one. That just happens to have a value of 1. The tangent of 0 is 0. And so by the time I do 1 divided by pi over 4, I end up with 4 over pi, which is approximately 4/3. So what did we just find here? What we just found is that the slope between this point, and by goodness, where is pi over 4? Well, pi over 4 is the halfway point to pi over 2. So what we just found is that the slope between these 2 points is about 4/3, and precisely it's 4 divided by pi is the slope of that line. So that's the #1 thing I want you to think here is average rate of change is measuring slope, 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 slope. So let's really emphasize that in our notebooks is that we're measuring slope. Because on this next question, I want to try to answer this next question without actually doing all the math behind it. So here's my challenge. Can we answer this question without actually having to do all the numerical number crunching to find the actual rate of change? And the question says, on which of the following intervals is the average rate of change the greatest? The first choice is from 0 to pi over 6. Your second choice is from pi over 6 to pi over 4. And your third choice is from pi over 4 to pi over 3. And we're trying to figure out which one has the greatest average rate of change. Well, in other words, what we're looking for is between which 2 points is the slope the greatest. We're looking for the greatest slope. It's all about slope, slope, slope. So let's see, and I try to cut out a portion of the tangent graph and zoom in on it. And so what I'll do is I'll try to color code. My first interval I'm going to do in blue. And I'm going to try to approximate where I think pi over 6 is about a third of the way to pi over 2. So I'm chopping this in thirds, and I'm picturing the slope between those 2 points. I tell you what, it's pretty steep, so I think that's going to be tough to beat. It's a good start. The next interval I'm going to do in green. And now remember, pi over 4 is the midpoint between 0 and pi over 2. So I'm going between these 2 points. And what I think is, I think the slope of the green line is steeper than the blue line. So right now, if I had to pick between blue and green, I'd go with green as having the greater average rate of change. And then last but not least, let's try to pick out a fun color here. I'll do the third interval here in purple. And let's see, pi over 3 is right here. And so if I went from here to here, that looks like it's even steeper than the green guy. So of the 3 line segments, I think purple's the steepest. And so the interval from pi over 4 to pi over 3 has the greatest slope, or the greatest average rate of change. Ladies and gentlemen, hope you had a great night. Hope you picked up some new things. I'd encourage you to continue to play around with that calculator and graph as many wild, crazy, bizarre functions as you can. Let your creativity run wild. Graph tangent, graph the tangent of 2x, or graph negative 3 tangent of x, and see what kind of impact those types of things have on the graph. And I think through that exploration on your calculator, you're going to teach yourself some invaluable key facts about that graph. So have a great night, and I'll catch you tomorrow.